Okay, so today we're actually going to look at the last lesson in the first part of the solutions unit. So this is a nice quick lesson. We look quickly at two topics. So the first topic is what are some things or some factors that would affect the rate of dissolution? So what that means is what are things that make dissolving faster? Now, the nice part about these things is they're things you've likely experienced before and you could relate to. So the first thing that would help something to dissolve faster is to stir it. Okay, so in all of these situations, think of like a hot cup of coffee or tea and you're adding sugar to it. Okay, so if you're adding a little bit of sugar to your coffee or tea, you're not just going to dump the sugar in and let it sit there. You're going to stir it and that will help it dissolve. And the reason it helps it dissolve is it brings the solvent particles and it allows those solvent particles to surround the solute particles more quickly, right? So as you stir it around, you're just bringing solvent and solute into contact more rapidly. The second would be heat. Okay, so again, imagine your hot cup of coffee or tea. When you have a hot or a warm solution, the particles are moving faster, right? So they have more kinetic energy when they've been heated up. So because they're moving faster, they're able to surround the solute particles faster. Okay, so you're going to dissolve that spoonful of sugar a lot more quickly in a hot cup of coffee or tea versus a cold one. And that's just because of the speed of the particles and their kinetic energy. And finally, surface area. So what you could relate to is adding a sugar cube to your coffee or tea versus like granular sugar, a spoonful of granular sugar. So if you break up the solute into smaller particles, that's going to make dissolving faster because dissolving happens at the surface of the solute particles. So smaller grains are providing more area for solvent molecules to kind of get at or attack. Okay, so your sugar cube has a lot less surface area than if you were to crush it up into individual grains of sugar, right? That's providing a lot more of that like solute surface for the solvent to surround, right? Because in the cube, imagine there's all those sugar particles on the interior of this cube that aren't exposed to the solvent. So it's going to be a lot slower because the solvent can only get at this outside part, right? If you crush it up, then all those grains are exposed to the solvent and therefore they can be dissolved more quickly. So that's definitely something you can relate to a little bit. Now, the last topic is what's known as colligative properties. So colligative properties are basically properties of solutions that change when you add more solute particles. Okay, so the more solute particles you add and the greater the concentration of the solution gets, the more these properties change. Okay, so colligative properties depend on the concentration So colligative properties depend on the concentration of solute particles in the solution. So the more solute particles that are dissolved, the more these properties will change. So the three properties that we're going to look at are vapor pressure, Okay, now what happens is vapor pressure is reduced as you add more and more solute particles to solution. Depression of the freezing point. So what that means is the freezing point is lowered as you dissolve more solute, and elevation of the boiling point. So the boiling point gets higher as you add more solute particles. So let's look at each one individually. So vapor pressure reduction. So adding a solute, so such as sodium chloride, salt, to a liquid causes the vapor pressure to, adding a solute such as sodium chloride to a liquid causes the vapor pressure to decrease. So what is vapor pressure and why does it decrease when you add something like salt? So let's imagine an Erlenmeyer flask that's closed on the top. And in it, this one just has water in it, okay? So water, if you let it sit in a closed container, some of the liquid water is going to evaporate. And when it evaporates, those water vapor particles fill this space above the liquid, okay? And those water vapor particles are going to bounce around and exert a pressure on each other and the walls of the container. Okay, that's vapor pressure. So it's the pressure exerted by the gas particles above a liquid. Okay, so now if you take the same container like this, and this time you put salt water in it, so it's water with sodium chloride dissolved. Now I'll get a different color here. Okay, so you've got, these are your dissolved ions in here. What happens is there's an attraction between those particles of water and the ions, right? They're attracted to one another. So the water molecules are attracted to the positive sodium ion and the negative chloride ion, and that attraction prevents them, prevents the liquid from evaporating. Okay, it still will evaporate to some degree, okay, but it will be a lot less because of that attraction in there, and that keeps more of the liquid in solution. So more of the water stays in the liquid form instead of evaporating into its gaseous form. So because of that, there's fewer particles up here and therefore less pressure. So hopefully those diagrams help you understand the concept a little bit. Okay, so now let's talk about boiling point elevation. Okay, and it's very much similar and connected to this vapor pressure concept. So adding a solute to a liquid increases the boiling point of the liquid. So why is that? Well, we just said that the solute decreases the vapor pressure of the liquid. And boiling actually occurs when the vapor pressure of the liquid equals the pressure above the liquid, or like the atmospheric pressure. So if the vapor pressure is reduced, it will take more energy in the form of heat for the liquid to boil. Okay, so another way to think of this is to go back to these containers here. Okay, so we know that just the pure water is able to vaporize more easily, right? It can change from liquid to gas more readily than when the solute is dissolved. And that is because of that attraction between solute and solvent particles. That attraction holds this in the liquid state instead of, and fewer water molecules escape into the gas state. Okay, so the same can be said for boiling. Boiling is a change from the liquid phase to the gas phase. So if there's a stronger attraction here holding the water in the liquid phase, you need more energy to break that attraction and break those water molecules out of liquid into gas. So you need to add more heat to this container than you would to this container to make it boil. And that's because you got to break that attraction. So that needs more energy. There isn't that same attraction here, so you don't need as much energy. You need less heat here, more heat here. So that means the boiling point is elevated. It's at a higher temperature. You had to add more and more heat to this one. So an application of boiling point elevation is adding antifreeze to water in a car engine. When you do that, antifreeze is a solution. So it increases the boiling point of the engine coolant, preventing it from so-called boiling over. Right? So because it's boiling, will boil at a higher temperature once that antifreeze is added, because that's a solution. It will boil at a higher temperature, so the heat from the engine isn't going to cause it to boil, because it's going to require a much higher temperature before it will boil. Okay, let's look at the last one, and this one is freezing point depression. Okay, so freezing point depression just means that when you add a solute, you decreases the freezing point of a solution. Okay, so why is this? Well, for a liquid to freeze, crystals need to form. And crystals are like a very ordered framework, like almost like a lattice. When you add a solute, that disrupts that nice ordered lattice, and it prevents crystals of pure solvent from forming, or makes it more difficult because they disrupt that nice, neat pattern that happens when something freezes. So for example, if we're just talking again about water versus salt water, okay, the salt water is going to freeze at a lower temperature than just the pure water. So an application of this is putting salt on roads in the winter lowers the freezing point of ice. And that's a good thing, right? Because that way you're going to cause the ice on the roads to freeze at lower temperatures. So therefore, it's not going to freeze at 0, it's going to freeze below 0. So that prevents the roads from getting as slippery. Now, this freezing point depression, normally in class we do a very fun activity of making ice cream. And we use this freezing point depression. So what we do is we make a bag full of ice and salt. So we add salt to ice to lower the freezing point so that we can achieve a temperature much below 0. And then we make our ice cream in a separate bag, but we add it to that. So in a separate bag, you've got your contents for the ice cream, and you put it into the salty ice solution. And that way you can get the ice cream to form like that frozen sort of ice cream consistency, because you can get a temperature of that icy, salty ice that's like, I think usually minus I forget what temperature we normally get, but it decreases it by at least 5 degrees Celsius, if not more. So I'm going to include that in today's post, just the instructions for how to make ice cream at home, and that way if you have the ingredients or you want to give it a try, you can do that.